first exercise is about setting bits, and by default setting a bit is writing a 1 into an appropriate bit position. So we have a shorthand signed integer variable a, and the task is set the following bits 0, 5, 9, 10, 12, 14, 15. We know that setting bits or writing ones into selected bit positions can be obtained using the bitwise OR operation. So the correct C++ instruction for this task will be like this: A equals A OR. Okay, it's very important not to make it just A OR, because this expression will be calculated and has to be stored back to the variable a in order to get any result from this operation. Now the problem is what we would put here, and what we put here is called a bit mask, and this is basically a binary number in which we will choose these selected specified bits, and in these bits we will write ones in every position. And if you remember well, hopefully you do, sorry, it's 1, 0, 1, 1. The truth table for all operation, 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 1. This means that if, for example, this is our mask, okay, wherever we put a 1 in the mask, so it is here and here, we'll get the result of 1. And if the mask is 0, so it's here and here, we will not change the original value. So 0 will give 0, 1 will give 1. So this is how we can get this result. But first of all, and this is the main aspect of this kind of tasks, we have to first of all find the binary mask that we will use here. And the first thing that I will do is to write a binary mask. As often happens with binary calculations, we will work from the right, so from the bit number 0 to the left, and because we have an unsigned value, short values, short is 16 bits long. So these bits are counted from 0 to 15, and it is very important to know that this is from 0 to 15, and actually both 0 and 15, so the first and the last bits are here, okay? But never count bits from 1. So what I will do, I will start from the right and move to the left. I will work bit by bit, okay? And I will just put a bit here and compare, before writing this bit, I will compare it with this list here. So the first bit to write is the rightmost bit, is bit number 0. Bit number 0 is one of those that we need to set. So the rightmost bit will be 1. Then we have bit number 1, but bit number 1 is not on the list, so I will put 0. Okay? Bit number 2, not on the list, so it is 0. Bit number 3, not on the list, so it's 0. After each group of 4 bits, I will leave a small space here just to keep it in order. So 0, 1, 2, 3. Next bit is number 4. 4 is still not on the list, so it's a 0. Number 5, okay? 5, attention, it's on the list, so I put a 1 here, okay? Then I will now try to do it a little bit faster. 6, nope. 7, nope. 8, after the space here, 8, nope. 9 on the list. 10 on the list. 11, nope. It's a 0. 12 on the list. 13, not on the list. 14 on the list. 15 on the list. And we have the binary mask now. 1101, 0110, 0010, 0001. The problem is that C++ does not accept directly binary values. So the next step is to translate what we have just done into something that C++ can understand. It does not necessarily mean that we have to find a denary or decimal value for this long binary number. Luckily not, because C++ can understand directly hexadecimal numbers, and hexadecimal numbers are easier to decipher from this binary combination here. So, one small trick that I will use, I will now write in the far right part of my whiteboard, I will write a table of all representations of 16 hexadecimal digits. It's just a shortcut, because I could actually do it faster. Write 0001. I know that this is, 1, 2, 4, 8, okay? So it's a 1, hexadecimal 1. And here is 1, 2, 4, 8, so the value of this, these 4 digits is 2. I could also do here 1, 2, 4, 8. It's a 4 plus 2, it's a 6, okay? And here 1, 2, 4, 8. 8 plus 4 is 12, plus 1 is 1, so it's a 13. 13, but again, well, there's no such thing like hexadecimal 13. It's a, let me count what kind of a value it is. 10, it's A, B, C, D, okay? So this is a hexadecimal D. But what I wanted to do, and actually I changed my mind on the way, because perhaps this is the primary way in which you should do it, but you could also do it perhaps a bit faster, particularly if you have a number of operations like this to do. And this is something you can do actually before the test, in tests, not perhaps in 2020, but in a typical in-class test, time is limited. So what you can do, you can prepare something. You can prepare a table of hexadecimal digits from 0 to F or 15, okay? And this uses a trick to quickly write consecutive binary numbers. So I will start from the least significant bit, so the rightmost bit, bit number 0. And in a binary system, this bit number 0 shows a clear pattern, 0, 1, 0, 1, 0, 1. So I will just put here 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. I need it 16 times because I need to generate 16 hexadecimal digits. 2, 4, 6, 8, 10. 0, 1, 0, 1, 0, 1. Is it? 2, 4, 6, 8, 10, 12, 14, 16. That's what I needed. Now, moving on to the bit number 1, or second in the order, but it is binary bit number 1. Okay, after bit number 0, we have now bit number 1. It has a very similar pattern, but with double zeros, double ones. So 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1. The bit number 2 will have a pattern like 4 zeros, 4 ones, and so on. 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones. 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones. And the final bit, the bit number 3, remember, counting from 0, 1, 2, 3, we'll have 8 zeros, 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. And we have a complete table now. I will just need to add labels showing the consecutive hexadecimal digits. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, and F. Alright, and if we had this lookup table before, then instead of doing this calculation here, 8 plus 2, 4 plus 1, we could just use it as a lookup table. 1, 1, 0, 1, my 0 is not the most elegant here. Okay, 1, 1, 0, 1 is clearly D as we calculated. And 0, 1, 1, 0 is here, 0, 1, 1, 0, 6. So we can just match hexadecimal digit to your short binary pattern. But the key message here is that if you have any kind of a binary notation, you can group bits, binary bits, into group of 4, and then you can translate each group of 4 into a single hexadecimal digits, and then we'll just rewrite this number, remembering that in C++ to tell that this is a hexadecimal form, you have to use the prefix 0x, 0xd, 6 to 1, semicolon, done. This instruction will set the bits 0, 5, 9, 10, 12, 14, 15 in the variable a, whatever the previous value of the variable a would be done. Our task number 2 is similar to the previous one. The main difference is that this time we'll clear the following bits. Okay? Clear a bit means to store a 0 in this bit. The bits this time are slightly different, 1, 2, 3, 5, 7, 10, 11, 12, but we are going to solve this task a little bit faster because we have this splendid lookup table with binary representation for each hexadecimal digit. So the first step is to think about what we really need here. So again, and this is a no-brainer because we know we need to change the value of the variable. Then we have to say the variable a will get a new value which is constructed with a, and now something else. So to get the clearing of particle bits, we need the AND binary operation, and we also need not operator. So it's AND not. Not will negate each bit in our bit mask, so that we can just create a simple binary mask in which in every position when we want to clear a bit, we'll put a 1, okay, and in the bits in a position which we don't need to do anything with this, we'll leave it as 0. So the mask will be identical procedure as previously. You could also make a mask that would be originally immediately negated, so you would put zeros at these positions and ones everywhere else, and in this case you wouldn't need this not operator here. But we will use the not operator, and therefore our mask is starting from the right hand side, and this is very confusing because here the first bit looks like it was a bit too clear. No, the first bit is in fact the 0 bit, and the bit number 1 is the second bit. So the first bit is bit number 0, so at bit number 0 position we have a 0 because we don't want to do anything with this bit. Then we have 1, 2, 3, 3 consecutive bits, 1, 2, 3, then 4 not, 5 yes, 6 not, 7 yes, 8, 9 not, 8, 9, 10 we have 10, and 11, and 12, and then 13, 14, 15, nothing happens here, okay? Now, we have this splendid lookup table, which means that we can now just look up for these 4 values. I just remind you that we now divide these binary digits into 4 groups of 4 bits each, and now 1110, 1110 is here, so that's the digit E. 1010 is the digit A, And I have to move our instruction a little bit down here. A equals and technology. A equals A and not OX. And what we will have here, 1100 is C, 0001 it's 1. So the mask is 1, C, A, E, that's here 1, semicolon. The second task is now complete. Okay, so here we have the third task. It looks a little bit more complex than the two previous, but it is not that bad after all. If in the variable A, all of the following bits, 8, 11 and 14 are set, or any of the following bits, 3, 7, 8, 11 and 15 are clear, then clear all the bits in the variable A. So first of all, we have here a test, okay? A test about the bitwise content of a variable. So a part of our solution must be the instruction if. And in C++, all the conditions after if should be put into a bracket. So, if in the variable A, all of the following bits, this is a typical so-called binary test. Binary tests are done using the AND operator, bitwise operator. But important thing to notice here is that a test is just reading the value of the variable. We don't want to change, at least not at this stage when we are testing, we are not writing anything in the variable. So we will not use, there is no point to use this part A equals. So it will be just sorry for that. This one may be better. A and OX, and here there will be a binary mask yet to be found. Okay. And what happens then when I test the variable with a mask, with a binary mask? The binary mask has ones at every place, at every bit position that I want to test. And these bits will survive. So it's like a filter. I will just filter out all the bits that I am not interested in, and I will only leave the bits 8, 11 and 14. And this condition here is that all these bits, 8, 11 and 14, should be set, so should be ones in them. So if they survive, they will be the bits with a 1 in them, and everything else will be zeroed. So in other words, if I mask the variable like this, what I will get will be this mask, because at every mask position, so 8, 11, 14, I will have ones if these bits were set before. So this should be equal to the same mask that I have calculated, or I will actually calculate, alright? So A and mask must be equal to the mask, and this is how you can test for all the bits to be set. And the second operation, we also have a second condition here, which will be connected with a Boolean OR, because if it is either one test or another test, so we have Boolean OR here, and the second part is also a test, so it will be A and 0x. This will be another mask that I will calculate in a moment. But what should happen with this another mask? We ask now any of the following bits are clear. Okay? Any of the following bits are 0. So we have any zeros in this case. This is actually exactly opposite situation to this. If all are set, all are set. Yeah, but if all are not set, not all are set, this means that any of them should be clear. So We can get various combinations here, but definitely will not get the same mask again. So in this case, my condition should be not equal to 0x my second mask. And let's go ahead from this point. We will get to this part, what to do if these tests are positive, clear all the bits later on. It's actually quite easy, as you will see in a moment. Sorry, I will change the color I'm using because this blue one is not a very good quality. Alright, so the mask 8, 11 and 14, okay? There will be a lot of zeros in the beginning because 8 is far away from the right hand side. So, in groups of 4, bit 0, the first interesting bit is number 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's very interesting bit. 8. The next one is 11. 8, 9, 10, 11. Okay? And 14. So 12, 13, 14, and 15. And the hexadecimal representation, that's a 0, that's a 0. 1, 0, 0, 0, 1 is here, it's 9. And 0, 1, 1, 0, it's here, it's 4. Okay? Of course, there is absolutely no reason why you shouldn't do this rather in this way, like 1, 2, 4, 8. 8 plus 1 is 9. You can find the values for these hexadecimal digits manually by calculation rather than lookup table, but with the lookup table it's a little bit faster. Just to have not so much variety of colors, I will go back to the blue. 4900, 4900, and 4900. The first part is done. Now the second mask. These are bits 3, 7, 8, and so on. So let's start. 0, 1, 2, 3. That's one of them is interesting for us. Then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? And now the hexadecimal representation. 1 triple 0 is 8. 1 double 0 1 is 9. 1 triple 0 is again 8. And 1 triple 0 is again 8. Oh, quite a funny representation. We have here, sorry I put it a little bit, I didn't leave any space here, so I have to move this stuff here, okay. Blue pen, it's 0x8, 9, 8, worse and worse. But it's 8, 9, 8, 8, not equal to, sorry, it got wet. Okay, so again, 8, it will be red, sorry for that, it's here, 8, much better with red, okay. 8, 9, 8, 8 is not equal to 0x 8, 9, 8, 8, and this is our condition. And now, if these two tests are positive, okay, we might have a rather long connotations with positive tests, but fortunately it's a binary test, not a coronavirus test. So what we do in case both these parameters are positive, so if both these conditions are positive, clear all the bits in the variable a, It's so easy. A equals 0. In those rare cases, you can avoid any bitwise operations and finding bitwise or binary masks. This statement is quite straightforward. Clear all the bits in the variable A. To clear all the bits in the variable A, I just need to stop 0. 0 definitely has all possible bits clear. So that is the final part of this presentation. The third task is now complete. Thank you.